Welcome back, everyone, to episode 4.1. Let's dive right into this explainer. As we touched on back in episode 1.3, the subsea umbilical is essentially the nervous system of an offshore field. Today, we're really going to look under the hood. We're opening it up to see what makes it survive years at crushing hydrostatic pressure without a single one of its dozens of internal lines failing. What we're looking at here isn't just some simple cable. It's a hyper-engineered, life-sustaining megastructure, precision-bundled so that every single component can survive an incredibly hostile environment. So, to really appreciate this engineering marvel, we've got to start with a huge fundamental conflict. How does a hollow tube survive the literally crushing pressure of the deep ocean without just snapping or buckling inward? Think about it for a second. The umbilical's entire job is to deliver hydraulic power, electrical signals, and chemical inhibitors from a host facility to every single subsea tree and control module in the field. It's the single physical link that makes remote operation possible at all. But it has to do this at extreme depths where the external water pressure would instantly flatten an ordinary steel pipe. And this brings us to the core physics at play. I want you to picture the difference between a crushed aluminum soda can and a highly pressurized scuba tank, both sitting at the exact same water depth. Both are hollow metal cylinders, right? But it's the wall thickness, the material strength, and the overall geometry that determine whether the external pressure crushes that cylinder flat, like the soda can, or whether it holds its shape indefinitely, like the scuba tank. Subsea umbilical design is entirely about engineering that scuba tank outcome. Section 1. Anatomy of the bundle. So how exactly do engineers achieve that scuba tank outcome across a cable that can run for absolute miles? Well, if we peel back that protective outer sheath, we see that the secret sauce making deep water umbilicals possible is a highly specialized material called super duplex steel. Why use this specific alloy? Because it offers a remarkably high strength-to-wall thickness ratio combined with incredible resistance to seawater corrosion. The underlying mechanism here is absolutely critical. A thinner-walled tube significantly reduces the overall weight of the umbilical and reduces its bend radius. It gives you the massive strength you need to hold back the ocean without turning the umbilical into an impossibly heavy, rigid rod. Inside this single cross-section, which, by the way, is often just a few inches in diameter, you've got multiple payload elements packed tightly together. You have your hydraulic small-bore tubes acting as the muscle, providing the physical pressure to open and close safety valves. You have chemical inhibitor lines acting as the bloodstream, preventing hydrates and corrosion, and you have electrical quads acting as the spinal cord, delivering power and transmitting data. A single mechanical fault to this bundle can knock out totally unrelated functions all at once, which is exactly why protecting them is paramount. Section 2. Surviving hydrostatic collapse. This brings us to the ultimate battle of this explainer. Those delicate, multifunctional internal lines versus the extreme, inward crushing forces of the ocean environment. The crucial point here is the sheer magnitude of the water pressure we are dealing with. At full ocean depth, the extreme hydrostatic collapse pressure squeezing inward on the jacket reaches tens of thousands of pounds per square foot. That is literally several tons per square foot, actively trying to buckle the hollow tubes inward over the entire lifespan of the field. The umbilical has to constantly, flawlessly fight off this inward crushing force while maintaining the integrity of every single internal service line. Section 3. The installation trade-off. So, if the pressure is really that extreme, a logical question arises. Why don't engineers simply make the protective walls infinitely thick? Well, doing that triggers the ultimate zero-sum game of subsea engineering. You literally cannot design an umbilical by looking at just one factor. It is a strict balancing act between three distinct things: hydrostatic collapse resistance, installation bend radius, and total weight. If you optimize for just one factor, say you make the walls incredibly thick to maximize collapse resistance, the total weight skyrockets, and the bend radius becomes so stiff that the umbilical physically cannot be spooled onto a reel or installed off a vessel. You have to satisfy all three constraints simultaneously, or the project fails before it even hits the water. And guys, the stakes for getting this balancing act right are absolutely astronomical. The umbilical is often the longest continuous piece of engineered hardware in the entire subsea field. Once it is laid on the seabed, it is notoriously difficult to inspect or repair. If there's a single installation mistake, or if a tube collapses because the design margin was miscalculated, bringing in a vessel to mobilize and repair it can cost well over $100,000 a single day. It's an economic penalty you simply cannot afford. Section 4. Future-proofing the field. Because those stakes are just so massively high, the most important economic decisions about this lifeline are actually made on day one of the design phase. So, I want you to think about this for a second. With all this complex engineering we just talked about, the super duplex steel, the extreme pressure calculations, the delicate weight balances, what do you think is the biggest, most common trap engineers fall into when sizing the umbilical cross-section? The answer? Failing to plan for spare capacity on day one. The absolute biggest mistake you can make is treating the umbilical as fixed infrastructure, sized only for your initial field requirements. If your field expands, say you add additional wells or you end up needing new chemical injection points years down the line, retrofitting additional capacity into an already installed umbilical is nearly impossible. Adding spare service lines right at the initial design phase is dramatically cheaper than trying to lay down a completely second umbilical later. So we've seen how the umbilical brilliantly acts as a nervous system, delivering control and chemicals while fending off thousands of pounds of external pressure. But I'm going to leave you with a bit of a provocative thought for next time. If the umbilical handles the controls, what conduit carries the actual highly pressurized, scorching hot produced fluid from the seabed all the way up to the surface? That structure is under attack from both the inside and the outside simultaneously. That, my friends, is the production riser, and understanding how it survives is a whole different level of engineering.